Welcome to Higher Structure Seminar Series. This is the last one of this season, let me say. And we thank Cem Yetismisoglu from Medipol University for giving this talk. He will tell us about graded manifolds and their applications in physics. And we thank Cem very much for giving this talk. Please, Cem.
Uh, İlhan Hocam, I thank you very much for inviting me. It's an honor to speak in your seminars, which have been going on for a while. So today, as you said, I will be talking about graded manifolds and their applications in physics. And this will be a very, I do not know, so very, I know this is higher structure seminars, and this may not be so higher structures in the realm of higher structures, but I'll be mostly focusing on supermanifolds and particular types of them, a particular type of them, and their applications, which has been in my life for a while now, since the last years of my PhD. And there are two projects, if time permits, that I want to talk about. The first one will be about applications of these manifolds to discrete dynamical systems. And then the second one will be about um, applications of these to symmetry structures coming from string and membrane models, and how these symmetry, so to say, algebroids are encapsulated, and what we have been doing with IB Kocan and my friend Kerem Can on these. Okay, so without further ado, let me start. Uh, this will be my outline. I'll quickly motivate what a graded geometry mean, and then I'll immediately focus on supergeometries, and I'll talk about them a bit more in detail and some structures on them, such as geometrical structures that will be of use to me. And then I will, in the last two parts, I will be talking about these applications that I've told you. Okay. So what I mean by a graded manifold is the following. At the end of the day, it'll be a locally ringed space, and it'll be a topological manifold with some sheaf of functions on it. The topological manifold will always be denoted by M, and then the sheaf of functions for me will be denoted by A. This A denotes the globally defined functions on M. And then I will ask that this sheaf of functions has some grading on it, and then this grading will be denoted by some group, and then mostly I will be interested in, so an example of by the way, graded manifold is just a regular manifold where the grading, there is no grading, there's trivial grading, so a group with one element for me. And then when you go to the next, what is the word that I'm looking like? The simplest non-trivial example of it will be a supermanifold where the sheaf of functions will be Z mod 2Z graded, the group with two elements. And then more generally, you can consider more general graded manifolds where the sheaf of functions can have a natural number grading, integer grading, some powers of these groups, okay, and so on and so forth. But I'll be interested in supermanifolds with possibly an N grading on them. Okay, so I won't go. This Z grading is a bit harder to understand on my end, anyways. And then there are some other versions of these gradings which are of use in physics that people consider as well. Okay, so why do people consider these? Mostly these can be understood as generalization of linear structures. So whenever you have some sort of an non-trivial grading on your sheaf of functions on a manifold, then you may want to understand, for instance, what are the automorphisms of these functions, algebras. So mapping suppose there are different degrees, or degree generators of these sheaf of functions. If you want to study automorphisms, then the natural type of automorphisms that you want to use will be the ones that respect the grading. And whenever you have a graded structure, you want to consider morphisms which map, for instance, if you have a degree 1 generator and a degree 3 generator, you may consider the cube of the degree 1 generators mapping to the degree 3 generator, respecting this grading. So having these different degrees in play will give you non-trivial, nonlinear generalizations of morphisms, nonlinear generalizations, which are controlled by the degrees, okay? So they can be understood as if you have a non-trivial grading, then you would have some sort of nonlinear transformations, but still controlled by the degree of generators. So if you do not have as many different degrees generators, then you will have types of morphisms which relate these particular degrees, so on and so forth. Once you start talking about your function, sheaf of functions to be graded, then you can start talking about um, um, also tensors being graded and so on and so forth. With these, your geometrical structures that you usually encounter over regular topological manifolds could be generalized to graded setting as well. And these are abundant also in physical applications. You can start talking about metric, graded symplectic, contact, tensors, shape forms or structures, or for instance, with a Z mod 2, Z2 grading, there are also homological vector fields that will be in play, for instance, for us, which will normally will not be there in the usual non-graded setting, okay? And on top, graded geometries can help geometrize certain algebraic structures. And I will be talking about this in the very last part of my talk. And through these homological vector fields, you can talk about, for instance, algebra structures or algebroid structures being also encoded through these certain homological vector fields, which are geometrical objects on top of these graded manifolds, okay? In particular, if you want to do physics, there are two types of particles in nature that we've observed so far. They are called bosonic and fermionic particles. And the dichotomy of these two types of particles can be neatly encoded at the level of supermanifolds. The two will be associated with the elements of this Z2, even and odd types of particles, if you like. And then whenever you want to study their symmetries, a very, how do you say, favorable type of symmetries, so-called a supersymmetry, which is a Z mod 2Z generalization of usual symmetry algebras or groups. So supersymmetries can be also nicely understood geometrically as well on top of super manifolds. And also these super manifolds, graded ones especially, appear naturally in quantization schemes when you want to quantize physical models. Then there are schemes that you use, a la Dirac or a la these Russian people, BRSD, BV, etc. And here, when you want to do this kind of operations, then naturally these graded manifolds with certain graded supermanifolds with certain geometrical structures on them will appear. Okay. All right. Let me dive into supergeometry immediately. Before doing so, I will talk about what a Grassmann algebra is. This is an important. This will be an important part of sorry, structure sheaf of functions over a supermanifold. A Grassmann algebra will be an algebra over reals or complex for us, generated by M non-trivial generators and a 1, subject to these M non-trivial generators satisfy an anti-commutation rule, okay? So if you take two of these, theta A and theta B, denoted by, and if you take their anti-commutator, they will vanish, all right? These are, due to this relation, these are 2 to the m dimensional algebras, finite dimensional algebras. Any element of this algebra can be expanded in powers of thetas, which are, there will be a degree 0 term, there will be a degree 1 linear in thetas, and then the top term will be degree m, theta 1 up till theta m multiplication, okay? This should be m, sorry, there is a typo. And the coefficients will be coming from the ground field R or C, okay? In these Grassmann algebras, by construction, there's a natural projection map called the body map. This, not many people probably call this the body map. I will be calling this the body map. It is due to some people, actually De Witt. This naming is due to De Witt, who is one of the forefathers of supergeometry as well. This body map does the following thing. If you give me an element of this Grassmann algebra, it just projects down to the base field. So if you think about these generators, 1, theta 1 up till theta m, this body map kills all thetas and keeps the 1, okay, only. And in this, if you give me this f, which is mixed, which contains all possible degrees in thetas, then it just maps it to the element which doesn't contain any theta, okay? On this Grassmann algebra, there are two degrees. There is a z degree and a z. There is a z grading and a z2 grading, which are compatible. The z grading is associated with the powers of thetas. If you have a multiplication of k thetas, then it is degree k in that sense. And then after the degree m, the rest of the gradings, after grade m, the rest of the grades are trivial. And then in this decomposition, you can also consider just even multiplication of thetas or odd multiplication of thetas. These also give you an even and an odd grading, okay? So where do we encounter Grassmann algebras? One of the most fundamental examples that I know is the alternating forms on a vector space Rn or Cn. If you give me Rn or Cn, then you can consider tensors on them, and you can consider the tensor algebra with the usual tensor product. Then if you quotient this by the ideal that the tensor product of any tensor given by this ideal, where you consider tensor squares to go to 0, then you obtain the alternating forms on this vector space Fn. And then the product of these, first of all, this quotient is denoted by lambda Fn, which is the Grassmann or the alternating forms on Fn, which is a Grassmann algebra itself with the wedge product, which is the totally anti-symmetrized tensor product, so to say. It's an anti-commutative associative tensor product, okay? So what is a supermanifold? Well, a supermanifold is first of all, it has two dimensions compared to the usual good old manifolds. A real n, m dimensional supermanifold is a pair where you have a usual smooth n manifold, and we will call this the body of our supermanifold. And then you have a sheaf of functions on it, and this sheaf of functions are Z2 graded. On top, you have a globally defined surjective body map, which eats a globally defined Z2 graded function and sends it to a function on the body manifold, okay, which is the smooth function on the body manifold. And then you ask that on top, you ask that this sheaf is locally trivial in the following sense. Whenever you consider some open set of this open covering of this smooth M manifold, then you ask and you call this U alpha, you ask the sheaf of functions on this open set look like or be isomorphic to the smooth functions on that open set tensored with lambda Rm, which is this was a real supermanifold, so you consider the Grassmann algebra with M generators, a real Grassmann algebra with M generators, okay? Now, this is a local thing, and can you understand? I mean, this lambda Rm, we said that this is actually a antisymmetric tensors on Rm. So can we understand this locally trivial condition from from a geometrical perspective? Yes. These actually local functions can be understood as sections of an exterior bundle, of a trivial exterior bundle. What do we mean by that? The local model will be denoted by Rnm, and you consider Rn as a smooth manifold. you construct a rank M trivial vector bundle on it, which is Rn times Rm. And then you consider the exterior bundle of this trivial vector bundle. And then you consider its sections, and it is denoted by this Rnm. Now, um, this is already what I told. There are n, so for the functions on Rn, there are n generators. For the functions on Rn, there are n generators, the coordinates on Rn. And for the exterior directions, if you like, there are m generators associated with the directions in the fiber. Okay. All right. Now, to understand the global structure of a supermanifold, you need to understand how these local models are glued together. Just like how a regular manifold can be understood by patching different, open sets and functions on them, if you like. You can ask what happens, for instance, if you give me these local models, how are they glued together? Okay. And then here's a picture. Um, Let me try to decipher what my picture is saying to you. So this is my supermanifold curly M. The black drawings correspond to our body manifold, which is good old topological manifold. And then the blue is called, if you like, a fuzz. Sometimes people call that, which gives us the nilpotent directions, the theta's. And then if you give me two open sets called U and V, on this open set, you have a trivial vector bundle. The coordinates on U will be called by X. The coordinates in the fibers on top of U will be called theta's. And then if you give me a red one, another open set with an overlap with U, then the local coordinates will be called Y and eta. And then you want to understand how do I glue these, if you like, functions on this open set to the functions on this open set, okay? Or generators, how do you glue the generators of the functions or the sheaf to the generators on the other sheaf, okay? Now, pretty much you want this to be an invertible transformation, and then you want to be satisfying certain more conditions called co-cycle conditions, maybe if you like. And on top of this, since these are graded generators, there's a grading associated with them. You want this automorphism to respect that grading as well. So if you give me the body coordinates in V, which are y's, should be even functions, degree 0 functions with respect to the Z mod 2Z grading. And then this enforces that this y should be a function in theta's, should have an expansion in theta's of only even degrees, in only even degrees, okay? And similarly for the fiber direction, this must be only in the, since this is odd, it must have some expansion in odd degrees, okay? Now, if you look at this, you see that there are these non-trivial terms coming, and then you want to study what sort of automorphisms in general you may get. And you can study them. People have studied them. The simplest of these is given by the underlined, the green underlined versions. So if y's are just immediately functions of x, just good old regular functions of x, and if ethas are linear in theta, these are a particular type of gluings that people like to work with. These are linear, so these are degree preserving. In general, you may consider more non-trivial degree non-preserving gluings as well. When you work with these degree preserving gluings, then first of all, let me say that these generators are immediately related to these generators, which are in a linear fashion. And this was a vector bundle, and that was another vector bundle. If you only use the underlined type of transitions, automorphisms, then this type of gluings are immediately related, I mean, are equal to a vector bundle gluing, okay? And this psi or phi ABs are nothing but these transition functions associated with gluings of a vector bundle taking values in GLM. Okay, and so this is a GLM valued cocycle. But of course, you can do more general things. When you do more general things, these are taking values again in another group, which is a supergroup denoted by GLNM. So these degree preserving morphisms or linear morphisms, when you want to work with them, the supermanifold data, the gluings of the supermanifold data is equivalent to the data of a vector bundle, okay? And such examples of supermanifolds, which are glued using just a vector bundle vector bundle automorphisms, are called split supermanifolds. And I will be interested in working with them, okay? So what is a split supermanifold? Split supermanifolds, as we said, are equivalent to the data of a vector bundle. So you first start with a vector bundle. The vector bundle, if you like, is a locally product space of a manifold with the fibers being a vector space. And then what you do if you give me a vector bundle is that you keep, so there are two types of generators for the sections of this vector bundle, the base directions and then the fiber directions. To obtain a supermanifold, and these are not graded, to obtain a supermanifold, you say that, okay, I'm going to change the degrees of my fiber generators and then give them an odd degree, shift their trivial degree 0 and make it into a 1, where this 1 is the 1 of a Z2, okay, the element 1 of a Z2 group, okay? And through this, you obtain a supermanifold, which is called and this grade shifting is sometimes called a parity operation that you apply to a vector space in particular, and then at the level of a vector bundle, you apply this to the fibers, being the vector spaces, and then you obtain the supermanifold through this. So this, since our gluings are linear in odd fiber directions, there's a natural grading globally defined on the sections of these supermanifolds. In general, this is not true. For a general supermanifold, you cannot have this. But for such split supermanifolds, there is a grading on their space of superfields. Superfields are just sheaf of elements of the sheaf of functions. These are in particular examples of graded manifolds, okay? And there are more general graded manifolds as well. This splitting can be understood as a projection map, which I'm not going to go into detail, but maybe I could say that here. Remember in our supermanifold definition, there was a globally defined surjective map, which we denoted with the epsilon. It took a general function, super function, and then it sent it to its body, which is a regular smooth function. This map has a kernel. The kernel is given by the nilpotent generators, sheaf of nilpotents, and then there is a short exact sequence that you can write associated to a supermanifold. Whenever this short exact sequence has a right splitting, it is that projection. And for the graded manifolds, that right splitting exists, and hence the name comes from there, okay? It is a seminal result of Batchelor, Marjorie Batchelor, that she showed that real manifolds are always split, okay? And there is another seminal paper by Jean-Louis Cozul, which says that if you give me an affine superconnection, which I will maybe later define, on a supermanifold, that will induce a splitting for you, okay? So it'll give you a vector bundle data for you, okay? But of course, split supermanifolds are not the end of the story, and there are many other examples of supermanifolds which are non-split, and these are not so exotic as well. There are also complex supermanifolds, and they may be non-split. It is shown by green. And also, for instance, sometimes for physical reasons, people study super Riemann surfaces and their moduli spaces. And Donaghy and Witten at some point showed that this moduli space of super Riemann surfaces is a supermanifold which is non-split as well, for instance. So you see examples of non-split supermanifolds as well, but we will not be working with them. I'm just saying that. So what are examples of split supermanifolds? We said that these are vector bundles at the end of the day. So pick your favorite vector bundle if that exists, and then by applying this parity shifting operation, you can obtain a split supermanifold. But there are also other supermanifold examples. For instance, any smooth manifold is itself a supermanifold where the bosonic dimension is equal to the dimension of the smooth manifold, and the fermionic dimension, the fiber dimension, is zero. So there is no Z2 grading, or sorry, I should say it this way. The Z2 has two elements, 0 and 1. There are no generators with degree 1 for a smooth manifold. Also, another example, extreme example, would be a 0m dimensional supermanifold, which is just a Grassmann algebra over a point. Okay, it has m odd generators and 0 even generators. So if you give me any manifold, n-dimensional, you can construct exterior forms on this manifold. And this is in particular an example of an n, n dimensional supermanifold. The usual functions are generated by x's, if you like, and then on a local patch, and then in the same patch, the differential forms are generated by dx, subject to the anti-commutation relations, okay? And more generally, as we said, you give me any rank m vector bundle, which means your fibers are m-dimensional over some manifold of dimension n. You can apply the parity shifting, meaning that you give me rank m vector bundle. Its base directions are, the functions in the base are generated by x's. The fibers has coordinates ya. And then a priori for a regular vector bundle, the degree of these generators in the fiber directions is 0. But if you apply the parity shifting, then the fiber direction generators, I will label them with theta a after parity shifting, and their degrees will be 1. And then this will give you the generators, the odd generators for the superfields, okay? All right. So on these split supermanifolds, you can talk about many things that you know from regular differential geometry. You can start talking about superfields, which are just functions. And then locally, they look like there's a body, which is just a smooth function, for instance, for a smooth manifold on the body. And then the rest of them can be expanded in terms of the odd generators, theta a's. Sorry. You can talk about functions. You can talk about supervectors, which are just the supervectors are defined by sheaf of graded derivations of these functions, just like in the usual regular differential geometry. They are a free module over the sheaf of superfields, and then you can show them locally in terms of derivative operators. The derivatives partial x and partial theta will be the generators for these vector fields. And they give you a Lie superalgebra under the graded Lie bracket. They generate flows. You can talk about a special vector field called an Euler vector field, counting the degree of a given superfield, so on and so forth. You can also talk about supercovectors. Covectors will be the dual of supervectors, pointwise dual of supervectors. And then they are again a rank m plus m free module. I mean, they are generated by dx's and d thetas. Here, I should tell you that my generators for the sheaf of functions are x and theta with degrees 0 and 1. For the differential forms or the covectors, the dx and d theta change character. Dx is an odd generator, whereas d theta is an even generator. And this is also in line with what we have from the usual regular differential geometry, okay? And then you have the graded tensor product, Z mod 2Z graded tensor product, and using that you can start constructing tensor powers of these tangent and cotangent sheaves, and then you can start talking about the supertensors on a supermanifold. Then, in particular, to do calculus on a supermanifold, you may be interested in superdifferential forms, which are graded antisymmetric supertensors on a supermanifold. Okay. Um, The superdifferential forms on your local model also has some degree, okay? And then locally you can write, I mean, on this, by the way, on this local model, everything is global. Everywhere x and theta coordinates are defined. But when you want to, of course, talk about these operators such as exterior derivative, interior product, and Lie derivative, you need to tell me how you glue them again. And you can make sense of them as a globally defined object after you glue them on the totality of the supermanifold as well. And this is indeed the case, by the way. Okay. The exterior derivative, interior product, and Lie derivative is there, acting on the superdifferential forms. The exterior derivative is again superdifferential form degree increasing. Interior product is degree decreasing, and Lie derivative is degree preserving. Lie derivative is defined through Cartan's magic formula. And then with the Cartan's magic formula, these three operators satisfy the six relations, the Cartan calculus relations, okay? So exterior derivative is nilpotent, interior product is nilpotent with respect to an even vector field. And the Lie derivative and exterior derivative commute. The Lie derivative and interior product close like this. When you commute them, it gives you an interior product. And the Lie derivatives also, when you commute Lie derivatives of two with respect to two vector fields, it's again a Lie derivative, okay? With respect to the commutator of these graded commutator, Lie derivative of these vector fields, okay? So you can see that these formulas, the way I written these formulas, they can be understood as super vector fields on a different supermanifold, which is you give me the RNM, you consider the cotangent bundle on RNM, and then you consider vector fields on the cotangent bundle of RNM, then these operators are elements there, okay? All right. And finally, one thing that I will be also talking about is that on a supermanifold, you have affine connections, which are just it eats a vector, it spits out a covector tensor a vector, okay? And it satisfies these two relations. It is when you feed in a superfield in the first slot, then the superfield immediately comes out. But if you feed in its second slot a superfield, then it has to satisfy this Leibniz rule, okay? You can understand these super-affine connections through these graded generalization of Christoffel symbols, okay? And then you can also describe them using connection forms, if you like, a la Cartan. And then you can define, given a super-affine connection, you can define its torsion and curvature through their graded generalized formulas. You have to account for the grading, okay? And as Kozlov said, when you give me a super-affine connection, then you can talk about a splitting on a supermanifold, just to remind. Okay. Now, there is one bit that I'm skipping here is that all of these are immediate generalizations of the differential geometry of smooth manifolds. On smooth manifolds, of course, you want to be able to integrate things as well. And to be able to do the integration on supermanifolds, I'm not going to describe this, but it requires a bit more care. It's not immediately generalized. The integration on supermanifolds is a bit different than the integration compared to the integration of on smooth manifolds. Okay. Now, what sort of geometric structures that we may want to consider on these smooth manifolds, say super manifolds, is that the first one I will be giving is a symplectic structure and a piece structure, if you like, induced from a symplectic structure. So I will give you a split supermanifold. A symplectic form on the split supermanifold is a Grassmann-Even 2 form, which is non-degenerate, meaning that its musical map that it defines from the tangent space to the cotangent space, the flattening map, is an isomorphism, and then it must be closed as well. Okay, such split supermanifolds equipped with a symplectic form having these properties will be called an even symplectic supermanifold, or equivalently a p-manifold. By the way, the notion of a p-manifold is more general than this, but they're defined on a graded manifold in general with a certain graded, uh, uh, uh, if you like, in terms of graded Poisson bracket. That's why it's called a p-manifold. But whenever you give me a split supermanifold, it's a graded manifold, first of all, and I'm giving you a symplectic structure which induces the Poisson structure. So in this setting, you can still talk about it's a particular example of a more general p-manifold, if you like, that people may have studied. Okay. So we said that the symplectic form is a two form, so we can expand it in the basis if you like, okay? And look locally, a two form will have dx, the forms will be generated by dx and d theta, and then the two forms will have dx squared, dx d theta, and d theta squared parts. And this dx squared part is an antisymmetric piece. This d theta squared part is a symmetric piece, okay? And this is important that it gives you a symmetric along the fiber two form directions, okay? We will later use this. By the way, since this is a closed two form, the Poincare lemma still works on supermanifolds, which tells you that this closed two form can be locally expressed as the exterior derivative of a one form, okay? And then you can ask questions such as, are there inequivalent one forms which gives you the same two forms, so on and so forth. And you can start talking about, for instance, Durham cohomology and things like that, okay? And they also exist. So on a symplectic manifold, supermanifold, there's a natural generalization of symplectic volumes, which will be called the supersymplectic volumes. When they exist, I say, because you may want to consider integration over compact bodies and so on and so forth. I'm not going to be dealing with them. Whenever this integral exists, I will call them a supersymplectic volume. The supersymplectic volume it'll have a supersymplectic measure, if you like, and then this measure will have two parts. The first part will be, if you like, a measure. The second part will be a particular superfield, which gives you the correct generalization. This Berezinian, or the section that I give you, is like a top form which can be integrated. And there is the natural superdeterminant of your supersymplectic form. By the way, this supersymplectic form being a two form can be understood in terms of a supermatrix, which takes values it's a supermatrix. I'm not describing what that is. And this is the superdeterminant of that supermatrix. If you know symplectic geometry, the symplectic measure looks similarly to this. There is the x1 to the x2n, which is the regular, Lebesgue measure in those local coordinates. And then you have the square root of determinant of omega next to that. And then this is the correct generalization to the supersetting. As you see in this generalization, all of the different parts of the symplectic form, omega, a, and eta comes into play. And then the next part is the capital theta, which is a particular superfield. This superfield is the top superfield. There are M generators, remember, on our supermanifold for odd generators. This is the top degree guy, theta 1 to theta m. And then there is the determinant, square root of the determinant of the eta part. This theta actually only knows about the fiber directions. It knows about the fiber part of the purely fiber part of the symplectic form and the fiber directions of the superfield only. There's no body to it, if you like. There is nothing that doesn't depend on the fiber. And then this can be understood as follows. Remember, for instance, what I said. The exterior forms can be thought as odd generators, thetas. If you think about it that way, this theta 1 to theta m is the top form. Okay? This is like dy1 to dym, where y's are like fiber coordinates before parity shifting. This is like good old volume form in the fiber directions, in a sense, okay? And you need this to obtain, so this is a super integral. You can first integrate the fiber directions, and once you integrate the fiber directions, having this part is important. You obtain the regular symplectic volumes defined in terms of the body of the symplectic form on the body manifold, okay? So this theta is a non-trivial ingredient in this. But nonetheless, you can define supersymplectic volumes on a supersymplectic manifold whenever they exist. Whenever you have a symplectic form, its inverse is a bivector. It's invertible because it's full rank. Its musical map, if you like, its musical map is full rank. It gives an isomorphism. You can invert it, and then the inverse will be a bivector, which is called a Poisson bivector, satisfying a homological condition. It's Scouten-Neuhaus bracketed itself, multivector bracket induced by the Lie bracket of vector fields, is 0. And then whenever you have this, you can consider the super Lie algebra of superfields. Okay, and this structure is important. Okay, whenever it exists, this symplectic manifolds give you the natural ground to study mechanical or field theoretical models in physics to describe their phase spaces. And having these structures is important from the perspective of quantization as well. These will be the geometrical ingredients that go into the quantization scheme of these models. And it is indeed the case, whenever you give me a Poisson bivector and a symplectic connection on a manifold, yes, symplectic manifold, you can talk about something called the deformation quantization of this symplectic manifold, whose sheaf of functions, regular product of functions, commutative product of functions, is generalized into a non-commutative product, okay? This is shown by Kontsevich for general Poisson manifold. It's a very important result. And then later by Bordemann, it was shown that you can do this also in the graded symplectic setting on supermanifolds, okay? Kontsevich is regular Poisson manifolds. Bordemann is supermanifolds result, okay? Uh, so what are the natural examples of symplectic manifolds? The first example is the cotangent bundle of any supermanifold is a symplectic supermanifold whose symplectic form is given by this. If you call x theta the local coordinates of the supermanifold, then p and eta to be the fiber directions in the cotangent bundle, then dx dp plus d theta d eta is a graded symplectic structure on this cotangent bundle, okay, which is closed, non-degenerate, so on and so forth, satisfying all the requirements. So any cotangent bundle is symplectic, just like in the regular case, okay? There is a nice characterization of split symplectic supermanifolds For us, sometimes we will call them p-manifolds by Rothstein in 90s. This is a similar analysis to the Marjorie Batchelor's splitting theorem in the case of real supermanifolds. He Here he studies, in this paper, he studies the structure of symplectic supermanifolds, split supermanifolds, and then he shows some general results. But at the end of the day, I'm going to be talking about a particular example. If you give me an even dimensional Riemannian manifold, which means there is some metric on it, equipped with a symplectic form as well, you do not need compatibility between this symplectic form and Riemann metric in any way, then the cotangent bundle of this regular manifold is a symplectic supermanifold whose symplectic form is given by this formula. It is the symplectic form on the body, and here the metric comes into play and the curvature 2 forms comes into play. So this symplectic form knows about the geometry associated with the Riemannian metric a lot. Here you have to introduce some stuff such as some Levi-Civita connection and then the covariant derivative of these fiber directions with respect to the Levi-Civita connection. But this closedness of this symplectic form is due to the Bianchi identities of your curvature. This is quite a nice example, okay? So any Riemannian manifold equipped with a symplectic form is whose, you give me a Riemann manifold with a symplectic form, its cotangent bundle is always symplectic, okay, with the following symplectic form. And also, as usual, with the symplectic manifolds, there is a Darboux theorem for supermanifolds as well, which tell you locally your symplectic form can always be brought, you can find coordinates x and theta if you like, such that your symplectic form becomes the standard symplectic form, which only has the dx dx and d theta part, whose coefficients are, this is a standard symplectic form, 0, -1, 1, 0, and then delta AB is just the diagonal Euclidean metric with ones on it, okay? Just numerical. So the next structure that I will be talking about will be a homological vector field and a Q manifold. So this geometrical structure again starts with a split supermanifold, which is a graded manifold, and you equip it with a vector field Q of degree 1, Grassmann degree 1, such that it squares to 0. This is an interesting condition because if you wanted to play this game at the level of regular manifolds, just the good old bosonic manifolds, usual topological manifolds, I mean smooth manifolds with some smooth vector fields, trying to satisfy the vector field squares to 0, then it's a trivial structure. It doesn't give you anything new. But once you go to the realm of super, and then you ask that a degree 1 supermanifold degree 1 vector field satisfies this condition, non-trivial conditions start to appear. For instance, if you give me in the local coordinates x, theta, you can expand your degree 1 superfield to be of this form, where QIA and QABC are just regular functions which only depend on the bosonic coordinates. Theta is degree 1, theta BC is degree 2, and the partial theta is degree -1 if you like, because of the canonical duality between them. If you ask that this Q becomes homological, two conditions appear. These two conditions actually encode the conditions of being a Lie algebroid. Okay, we will come to that later. I'm just telling you. But in general, why are these important? If you give me a homological vector field, since it squares to 0, you can start talking about cohomology associated with this Q structure. Because it's a vector field, it acts on the superfields or the functions on your manifold, And then you can talk about the cohomology. And since this is a, sorry, this is a uh, graded manifold, you can talk about the kernel modulo image in different grades, and then you can start talking about the cohomology associated with this homological vector field. These cohomologies, and this is completely geometric, by the way, right? I give you a manifold, I give you a vector field on it, and I ask it satisfies certain things. This you define a cohomology using a vector field, which geometrizes the cohomologies, and usually cohomologies appear as, I mean, come as algebraic definitions. So you can think of this somehow geometrizing those algebraic definitions. So what kind of examples can I give you? Well, on any smooth manifold, a natural cohomology to study is the Dörum cohomology, right? Which is the cohomology associated with the coming from the exterior derivative acting on the differential forms. You can mimic this using the supermanifold, which is the cotangent bundle again, okay? So you give me the smooth manifold, you go to its cotangent bundle, but now you view it as a supermanifold, a shifted tangent bundle, if you like, whose coordinates are x mu, and then whose differentials are now differential one forms are labeled by these theta odd directions. Once you give me this supermanifold, the superfields on the supermanifold are mixed degree differential forms on the usual regular bosonic manifold that you started with, the smooth manifold. You can write down a degree 1 homological vector field, Q, which is theta mu partial partial x. Okay. If you square this, this is immediately 0 because partial partial x commute with each other, but theta's anti-commute, so the q square will be 0. This is just a Dörum differential on M. If you write, for instance, theta mu to be dx mu, this is just the exterior derivative operator acting on a differential form in the coordinates of your bosonic manifold. The cochain complex that you can define using this q acting on these superfields on M, which is just the differential form, is just the Dörum complex, okay, of the differential forms on M. So you can recover the Dörum cohomology of a bosonic smooth manifold using the cotangent bundle seen as a supermanifold equipped with a homological vector field, which is this, okay, degree 1. Now, you could also do the Lie algebra cohomology as well. Lie algebra is a vector space equipped with a bracket which satisfies the Jacobi identity. The Lie bracket is antisymmetric, so on and so forth. Suppose you give me the Lie algebra to be the frac G, which has a basis, the generator's EIs, and with respect to the bracket, Lie bracket, these are the structure constants of this Lie algebra. Then you can construct a supermanifold from this Lie algebra where you shift the degrees of this. I mean, you consider this to be a vector space over a point where your good old EIs are now declared to be degree 1. And then superfields on M are alternating forms on G. Okay, mixed alternating forms on G, sorry. Then you can cook up this degree 1 homological vector field. This is degree 1 because thetas are degree 2. Thetas are the parity shifted versions of E's, I'm sorry. And then this is degree 2, this is degree -1. The total thing is degree 1. And Q squares to 0 because this is a Lie algebra bracket and it satisfies the Jacobi identity. Some combination of F squares add up to 0. And that is equivalent to the fact that this Q squares to 0. SQ is, if you study Lie algebra cohomology, people construct the Chevalier-Eilenberg differential, the Chevalier-Eilenberg complex and the differential. This Q plays a role of that differential on that Chevalier-Eilenberg complex. Okay, and then you can start studying the cohomology, Chevalier-Eilenberg Lie algebra cohomology, using this Q instead, where G is now seen as a supermanifold with the shifting. Okay. All right. Now, if you have a Q structure and a P structure in town, which is a vector field and a symplectic two form, there is one more natural thing to ask as well. If you have both of these in town, you could ask that this Q structure respects the P structure in the following way. The Lie derivative of the symplectic form with respect to your Q structure vector field vanishing. Whenever this compatibility also appears, these graded manifolds are called QP manifolds, okay? Um, So whenever you have a symplectic form in town, there are natural vector fields that you can construct, which will preserve that symplectic form through the Lie derivative. And one example class of such vector fields are called Hamiltonian vector fields, which are determined in terms of a function, superfield. So whenever sometimes people approach these QP manifolds as follows. You give me a P structure, which is just a symplectic structure, if you like, of a certain degree, and we are not caring about the degree for the purpose of this talk. Then you define a Hamiltonian vector field through a Hamiltonian function using the inverse of the symplectic form through this usual formula of a Hamiltonian vector field. You take the exterior derivative of your Hamiltonian function, which gives you a one form. You invert using the Poisson bivector, which gives you a vector field. This vector field, by construction, preserves your symplectic form. Therefore, therefore, it gives you a Q structure, as long as you arrange the degrees properly, but you can always do that, okay? Whenever you want to, for instance, study some sort of quantization scheme, there is something called the classical master equation. And this classical master equation can be understood in terms of a QP structure where the Q structure is coming from some Hamiltonian. Okay. And for these QP manifolds, they play a key role in constructing certain classes of topological field theories called AKSC field theories. Okay. And these AKSC models have important examples in them, such as Chern-Simons field theory, Poisson sigma model, Courant sigma model, so on and so forth. Okay, so these are field theories that are assigned to sometimes some algebraic data, such as a Courant algebroid, or some manifold data with a geometrical structure, such as a Poisson manifold, P structure, so on and so forth. Okay, and they play important role in understanding things. For instance, earlier I told you that Kontsevich uh, showed that any Poisson manifold can be deform quantized, deformation quantized, and um, it turns out that you can understand the deformation quantization from the perspective of a Poisson sigma model as well. This is due to Cattaneo and Felder, and this is an important result, okay, as well. Anyway, so I don't know what my time is, how my time. Oh my God. Hocam, can I ask you a question? It's 8 o'clock, yeah. I've been
Uh,
so slow. Um, what
so
can I do? What do you suggest I
uh,
do?
let's give 10 more minutes.
Okay, I'll be try to be quick, yeah. I have not realized I was so slow. I am so
And
sorry.
then, no, no, no, it's going very good actually. And then you continue in full terms higher structures.
I would be happy to do that. I mean, I would have to do another 1 hour recap of this
Yeah.
talk. Okay, but okay, sorry. I'll try to be quick.
No,
Okay?
that's fine. Yeah,
All right. All right.
10 minutes, let's say.
Okay. So far, the things that I explained has nothing to do my work. These are like sort of the general geometrical background, the graded geometrical background that I will rely on. And then let me be quick. In the first study um, that I wanted to talk about will be a generalization of classical mechanics to discrete systems. When you want to study classical mechanics, the phase spaces are given by symplectic manifolds, and then you can start studying quantization of models and things like that. Um, in our first application, when you want to do, sorry, and when you want to do the regular classical mechanics, it's just a smooth symplectic manifold with some Hamiltonian function giving a Hamiltonian vector field, giving you the evolution. Okay, and then you can talk about observables with respect to states, giving some sort of expectations, doing measurements, so on and so forth. Okay. But the key point is that you work on a symplectic manifold. What happens if you go to a super manifold equipped with a symplectic structure? You remember on the super manifold, the sheaf of functions are generated by some bosonic generators xi's and some fermionic generators theta a. Well, the Grassmann algebra with m generators has dimension 2 to the m. Now, if you consider m coins, which can take values heads or tails, the possible state space is dimension 2 to the m. Then a natural question appears. Can you describe, if you give me m bits, which are m heads or tails, coin flips, coins, with possible 2 to the m states, can you encode the information of this probabilities of all possible probabilities of these coins into a superfield whose 2 to the m degrees of freedom, if you like, distinct degrees of freedom or possible states, will be related to the 2 to the m possible, expansion coefficients in this Grassmann algebra or in this graded algebra. And then can you do measurements? Can you do dynamics in terms of geometry? Okay. This is not new, but we have been able to manage with the generalization of the notion of a symplectic manifold, the usual symplectic manifold, by changing the symplectic form being from non-degenerate to maximally non-degenerate. You could first encode dynamics, and on top, by doing some other non-trivial constructions, you can come up with the measurement theory of them. I will give you a picture immediately, or maybe I will just say about this. So if you change the symplectic manifold definition from a manifold equipped with a two form to a manifold equipped with a manifold equipped with a non-degenerate two form to a manifold equipped with a maximally non-degenerate two form, which is again closed, then a dichotomy appears. The dichotomy is this. When you tell me a symplectic manifold has a non-degenerate two form, it enforces that the dimension of your manifold is even dimensional, is even. Whereas if you say it's maximally non-degenerate, the dichotomy appears that sometimes if your manifold is even dimensional, it'll be non-degenerate. If it's odd dimensional, it'll have a one-dimensional kernel. Okay? It turns out this one-dimensional kernel of the symplectic form can be understood as a vector field locally giving you a flow on your manifold. Okay? But the problem is, okay, you can describe dynamics using such an odd dimensional symplectic manifold. But the problem is, since it's odd dimensional and the symplectic form is degenerate, having one dimensional kernel, you cannot do measurements, symplectic measurements, using such a form. Well, we have encapsulated the dynamics and measurement theory on supermanifolds to the following picture. You start with an odd dimensional symplectic manifold, which is a one-dimensional kernel. This kernel will locally give you vector fields, which will generate the flow, which is the evolution. And this is if you know the geometric version of classical mechanics, this is the generalization of the Liouville equation for classical mechanics, which appears in Kopman von Neumann formalism, for instance, if you know about that as well. Then, to do measurements, you consider, just to restrict ourselves, you consider codimension 1 hyperplanes embedded into this odd dimensional manifold, codimension 1 hyperplanes, which are even dimensional. such that when you pull back your symplectic form onto these hyperplanes, it'll be non-degenerate. Therefore, there will be a symplectic volume on them. And then using this symplectic volume, you can do measurements. You can take integrals as long as you're doing things compactly supported, so on and so forth. Okay. And then if you start with, and we call these even dimensional non-degenerate, even dimensional submanifolds, which have non-degenerate symplectic form, we consider you can consider their evolution via the flow generated by the kernel of this odd dimensional symplectic form as well. So you can have, I mean, the description of states is a bit complicated, but you can start with a prepared state on a lab. You can evolve the state using the flow kernel. Then you can go to a later time, and then you can do measurements still on the, if you like, any lab or a lab which is given by the propagation of the initial lab in terms of this vector field rho, identified rho. So we've been able to do that. Uh, if I have 5 more minutes. And then there is nice enough questions that we're trying to tackle still, like since we are able to do these, and we are able to do these globally on a split supermanifold, equipped with a symplectic form and a torsion-free symplectic connection. What can we say more about these measurements? Actually, we are trying to tackle these questions these days, and it is very hard because probabilistic interpretation requires positivity and things like that. But the algebra of functions on a supermanifold, sheaf of functions on a supermanifold it doesn't play nicely with positivity because of the Grassmann anti-commutation relations. Minuses may appear, and then it may destroy your positivity that you may have worked so hard under the flow generated by the symplectic forms kernel, whatnot. So you have to somehow come up with manifestly positive things, and then you have to somehow stay in the realm of classical mechanics. This is tough because quantum mechanics, although non-commutative, it is in the realm of positive. I mean, like you can talk about measurements in quantum systems, so on and so forth, and these have been done there for discrete systems, and we are borrowing things, but we are trying to understand what can we say about the classical side more, and this is really hard. Sorry, I couldn't explain myself very well, but maybe I could do that later with more results in the right directions later. And we are also trying to understand certain models that appear there, okay, coming from these. On the other hand, when you study string theories, for some reasons, there, whenever you talk about closed strings, two types of fields appear, a metric and a B field, a two-form field. And then the symmetries of such models, when you want to study symmetries of such models, the symmetries are generated by vector fields for the diffeomorphisms and one forms for the generating gauge transformations associated with the two-form field B. Okay, and then when you want to combine these symmetries, it has a vector part, it has a one-form part. So the right vector bundle that you want to work with is the tangent plus cotangent bundle. And there, whenever you have some symmetry structure, you want to understand what sort of an algebraic structure that it gives you. For instance, whenever you have just the vector fields generating symmetries, you are considering the Lie bracket of these vector fields. So what is the correct bracket on this vector bundle which captures this symmetry structure? It turns out to be a Courant bracket, which is a more involved bracket than just a mere Lie bracket. On this tangent plus cotangent bundle, you can write a Courant bracket or equivalently a Dorfman bracket, which involves the Lie bracket plus the action of vector fields on those forms. And then this puts you in the realm of algebroids, okay? And then and these algebroids, as I noted earlier, can be studied in terms of Q structures. Q manifolds, okay? And with the derived bracket construction on supermanifolds, a la Kozman-Schwarzbach, we have been, with Kerem and Aybike Hoca, we have been working on to understand rather general algebroid structures associated with these stringy symmetries coming from stringy symmetries, but the generalization requires for you to consider not just vector fields and forms, but sections of some vector bundle and sections of another vector bundle which are not dual to your initial vector bundle. And then due to this not being dual, will like is one of the generalizations that we're trying to tackle. Well, people have studied these symmetries in the case where, or these algebraic structures in the case where they only consider a vector bundle direct sum a dual vector bundle and an algebraic structure on the direct sum in terms of the original ones. These are called the Drinfel'd doubles of algebroids with some, okay, I'm skipping many details, unfortunately, sorry about that. But we have been generalizing this, and they have done these work using supermanifolds, okay? And the most general algebraic structures have been called proto-bialgebroids for dual algebraic structures with some compatibility on them. And they have been studied by Reutenberg at the level of some QP manifold, okay? We have been not using the supermanifold, but we have been using these algebraic axioms as our guiding uh, properties to study whenever you give me a vector bundle A and a vector bundle Z with algebraic structures on them, we ask this following question. If you consider the direct sum of A and Z, let's denote that by E, and put an algebraic structure on this direct sum, through some anchor and then a rather general bracket, and ask that this direct sum satisfies certain other algebraic properties that you may desire coming from physical interests, what can you say? Okay, so we called this the Drinfel'd double associated with A and Z, and then we did this through introducing calculus based on Kerem's earlier work. And then we have shown that these calculus structures actually appear, and some non-trivial constructions that people have already worked on in physics can be understood a la the calculus that we introduced. And then we have obtained a genuine generalization of these proto-bialgebroids, bialgebroids, Lie bialgebroids, proto-Lie bialgebroids, to the case where the vector bundles in the summand are not necessarily dual and satisfying some bunch of all of these axioms, okay? And then we are trying to understand this mathematical algebraic framework that we constructed. What can we say in the physical cases of interest? For instance, for there are these exceptional Drinfel'd algebras that people have constructed for the sake of studying U-dualities, which is dualities associated with membrane models coming from stringy or M theories. And then they came up with these algebra structures, which are examples of Leibniz algebras. What can we say about these algebra structures in the case of our calculus and algebraic property setting for the Drinfel'd double of these, so to say, bialgebroids, okay? We're trying to understand these, and hopefully we will get to some models as well associated with maybe this AKSC constructions that I may have glanced upon earlier. So people have been using graded manifolds to describe algebroids, and we have not done that. We have understood their work, and then we have generalized their work by means of vector bundles and natural operations on them. And these natural operations mimic the operations of Cartan calculus. So therefore, we put some calculus conditions and operators satisfying Cartan calculus type relations, generalizing the Cartan calculus, and giving you these more general bracket structures. And if you enforce that these more general bracket structures should satisfy certain axioms such as Leibniz rules, I don't know, Jacobi rules, symmetric part decomposition, so on and so forth, what should be furthermore imposed on these operations? Okay. We have analyzed these and then we are trying to look for physical implications where people have already worked on, and then we are trying to put their work, explain them from our perspective in our framework. Okay. Sorry about that. So I think I'm done. Thank you. That
Oh,
was very
thank you
quick.
very much, Cem. Any questions or comments? So this Friday, Keremcan will be telling us about algebroids
Yeah.
in the institute.
Okay. Yani I'll try to be there hocam.
Yeah.
Uh,
So these are related to higher categories also.
Apparently, I mean, maybe İlker can answer this. So, hocam, L-infinity algebroid structures can be understood from the perspective of n-graded manifolds with some Q structures on them. And these probably have some relation to higher categorical. I mean, from what I understand, I don't know category theory very well. You define something, and there is a categorical generalization and understanding of it properly. Probably. Okay, from what I understand. So maybe İlker can say more though yani.
Yani hocam when you drop manifold structure condition, when you work with drive schemes, stacks, and something like that, of course, then you just shift to the framework of drive symplectic geometry, for instance.
Oh,
But even in the smooth setup, for instance, L-infinity algebroids, I guess they are kind of local models for differentiable stacks. So therefore,
Hmm.
even in that setup, you can formalize everything using stacky, constructions. Because smooth differentiable stacks can be formalized in terms of L-infinity algebras, as far as I remember, something like this.
very good.
And yeah.
Yeah. So any more questions or comments?
I have one comment.
Yeah.
Hello, everyone. I'm Kerem. About this higher categories, this B field that Cem showed, this B field can be seen like a connection on some two category or some connective structure. So these, even the fields are really encoded in these higher category stuff. We didn't deal them too much, just some technical details for us, but it has some close relations, and this AKS model 2 is directly related to this L-infinity structures, as İlker said, and these are directly higher categories, and even infinity categories appear in some natural sense. So that's the comment.
Thank you, Kerem.
So,
See you on Friday, by the way.
yes, see you in Friday.
Yeah. Okay. So this was our last seminar talk of this spring term. So we will start again in the fall term of 2006. But it may happen that we may have irregular seminars. So if that's the case, at any rate, we will announce. So I am closing the recording now.